Hey everybody, we are going to finish chapters 10/11 with this final lesson on 11.2. Before we jump into 11.2, I do want to address a couple of questions that I anticipate you having on the 11.1, 11.2 homework, and specifically on number 2, where you're sketching the graphs of these 3D graphs. So in part A, you're asked to sketch y equals -3. If you remember from class, we talked about if you just have a single, like when we were in 2D land and we just had something like y equals -3, that's just a line through y equals -3. So in 3D, though, it's not just a line because there's a second dimension that it doesn't matter what it is, it doesn't matter what x is, and it doesn't matter what z is. Regardless of the value of x and z, y is always -3. So that means it's going to be a plane through y equals -3. And these are tough to draw, so I usually it's basically a parallelogram is how I usually sketch it to represent this plane cutting through -3. So then in part B, we have two equations that we want to represent this system of equations at the same time and see what that looks like. So we're combining x equals 3 and y equals 4. So think about what that would mean. We're talking about a plane, so that would be an x equals 3 would be a plane through x equals 3, so 1, 2, 3 right here. So imagine taking the whole front, if you remember calling this the whole front wall, the YZ plane, and just scooting it towards us, shifting it forward 3 along the x-axis, and then y equals 4 would be similar. We'd be taking this zx plane and shifting that up 4 on the y-axis. So to kind of map that out on here, imagine again taking this whole front wall and we're just shifting it towards us positive 3 on the x plane. So that front wall is just closer to us by 3 units. And then what we're going to do is take this whole ZX plane, so kind of like, this side wall, and we're going to shift that up on the y-axis by 4. And the result of that are these two planes. So we've got the x equals 3 right here, and we've got the y equals 1, 2, 3, 4 right here. So we've got two planes intersecting over here right now. And if you think about when these two planes intersect, what's happening is it's forming a line, kind of like a corner, that forms an entire line when, if you think of two pieces of paper intersecting, where those two pieces of paper would intersect would just form a single line with those two flat planes. So that's what that results in. Again, it's really hard to talk about these three-dimensional graphs on a 2D surface, so this may be something we talk about again in person just because it is hard to do that when I can't even kind of demonstrate it for you guys in front of you. This last graph on part C, x squared plus y squared plus z squared equals 25. Hopefully you recognize that that's the equation of a sphere. If we took out that z squared, it would just be a circle with radius 5. Now we've got the third dimension, a sphere with radius 5. So the easiest way to graph that is to do the YZ plane, because that's the plane that we're looking at head on. And imagine it is just a circle, and we can graph that first. But then we also know that it goes back 5 on the x-plane and out 5 out here. So what we can do is kind of just make that look like a three-dimensional object by some extra lines here. So this is just a sphere centered at the origin with a radius of 5. Okay, I'm not going to cover any more homework problems. You are only asked to do 1 through 5. Okay. So if you do have questions on these, just circle them before turning them in Yeah, and we can talk about them next class. So let's jump into 11.2 and finish off this chapter. Okay, so 11.2 is on vectors in 3D space. We've already covered vectors in 2D space. We've talked about dot product, scalars of vectors, magnitude or length, adding and subtracting. And the great news is that all of these operations are the exact same in 3D space. So if we look at part A, so now that, first of all, let's look at our two vectors right here, u and v. Those now have three different components to them. When we add those together, we still just add each of the components. So I add the first component together, the second component, and the third component. So I'm just going to kind of quickly breeze through these formulas since they are not new. So u plus v would just be adding up each of the u1 plus v1. That would give me the first component. The second one is u2. Sorry, that looks like a v. u2 plus v2, comma, u3 plus v3. Okay. Note to self to change those letters. Okay. K times vector u. That's just a scalar on vector u. So all I would be doing is applying that scalar k to each of the three components. So it would be k times u1, comma, k times u2, comma, k times u3. So very simple and straightforward. Dot product also is the same. So if you remember from a 2D vector, you took the first two components of each one, multiplied them together, and then added that to the product of the other two components. Now we just add on the third components to this. So this is u1 times v1 plus u2 times v2 plus u3 times v3. Let's see, the norm of a vector, again, same idea. It's basically the distance formula, same way we would compute r, and that is the square root of the three components individually squared. So that would be u1 squared plus u2 squared plus u3. So this should look familiar because it's basically the distance from any point to the origin in 3D space. And then opposite of vector u down here would just be distribute that negative through each of the three. So negative u1, comma, negative u2, negative u3. So very simple, very straightforward. All of this behaves in the exact same way that vectors do in 2D space. All right, so let's just work through a couple of examples here then with actual vectors. So here we've got u and v. So if we do u minus v, remember we do vector subtraction with vector addition, so that would actually be u plus negative v, however you want to think of it. That would be 5 minus 2, negative 1 minus 0, 1 minus 4. So that would be the component, or the resultant vector would be 3, comma, negative 1, negative 3. Okay, this next one, u plus 1/2 of v. So that's going to be just good old u, 5, negative 1, 1, plus half of vector v. So we would distribute that 1/2 through to each component. So 1/2 times 2 is 1, 1/2 of 0 is 0, 1/2 of 4 is 2. So those are what we're adding together. 5 plus 1 is 6, negative 1 plus 0 is negative 1, 1 plus 2 is 3. All right, let's do dot product. That's a little more exciting. So u dot v. I'm not saying u times v because we're going to learn a new product, a new type of product with three-dimensional vectors today. So u dot v would be, remember, this does not result in another vector. It just results in a number that helps us determine the angle between vectors. So that's going to be 5 times 2 plus negative 1 times 0 plus 1 times 4. So we end up with 10 plus 4, so this dot product is 14. And then lastly, the norm or magnitude of vector v, and that would be the square root of 2 squared plus 0 squared plus 4 squared. So we get the square root of 20 right here. 20 is 4 times 5, and the square root of 4 is 2. So this has a magnitude of 2 root 5. Okay, so I flew through all of that just because none of these concepts are new. So now let's look at angle between two vectors in 3D space. We've already covered the formula for the angle between vectors in 2D space, and I have great news for you. It's the exact same thing in 3D space. So if you have two vectors and you want to know the angle between them, the cosine of the angle between them is always their dot product, u dot v, divided by the product of their magnitudes, u times magnitude of v, and then you would just do inverse cosine of that entire fraction right here to get the value of theta. Additionally, we can still talk about orthogonality, or if two vectors are perpendicular or not, with this same exact concept we did in 2D space. Two vectors in 3D space are also orthogonal or perpendicular if and only if their dot product is 0. So all of that applies. So that would mean u dot v equals 0 if they are perpendicular. Okay, I'm going to skip example 2 for now. We may come back to this. Kind of want to get to a couple of another new concept on the next page that's a little bigger. This example here is just practicing distance. It sets it up in terms of a robot moving an object from one point in space to another point in space, figuring out at which point the robot's arm is more extended. You're just finding the magnitude of each of those and comparing. So these just follow the formulas we talked about above. So I'm going to skip it for now. If I finish with a lot of time left over, we'll come back. But let's look at the next page first. Okay, in example 3, we're simply asked, are vectors u and v orthogonal? Again, so that's a very simple process as it was with vectors in 2D space. To determine if they are orthogonal or not, we're checking to see if their dot product is 0. So we're going to do u dot v, and when we do, that's 3 times 4, which is 12, plus negative 1 times negative 5, so positive 5, plus 2 times 6, which is 12. So we end up with 12 plus 5 plus 12, which is definitely not 0. So no, these two vectors are not perpendicular or orthogonal. Example B is still referring to the same vector u up here, but it's saying find p so that this other vector is orthogonal to u. So what that means is we're going to set up an equation basically because we want vector u and this vector to be orthogonal, so we're going to apply the dot product, which will form an equation for us. So we would do 3 times 3, that is 9, plus negative 1 times p, so that's just negative p, plus 2 times negative 2, which is negative 4. So that's just the application of the dot product, and if we're finding it so that they are orthogonal, we have to set that equal to 0 in order for that to happen. So we've got 9 minus 4, which is 5 minus p equals 0. We add p over, and we get that p must have a value of positive 5 in order for those two vectors to be orthogonal. All right, so now we get to something brand new down here called the cross product. So we are not talking about dot product. We are now talking about cross product and what a cross product, first we'll talk about notation, sorry. Okay, so the cross product of u and v. So first of all, we notate that with u and then across v. So it's different from dot product, obviously, because instead of a dot, we put an X there. So the names match very closely with the notation. Before I show you the formula for cross product, I'm going to show you what it computes first. Okay, so I had to remove a bunch of stuff because this keeps giving me technical difficulties. So let me jump back in here. So we've got the cross product of u cross v, so that would be vector u cross vector v. I will show you the formula, which is pretty complex, but first I just want you to understand what it's used for. So the cross product computes a third vector, so it's a new vector that is orthogonal to both of the original vectors. So these two vectors up here, u and v, when we do the cross product on these two vectors, it results in a third vector that is orthogonal to both of those at the same time. This is something that is hard to explain just verbally and not show you physically in front of you with like pens or my arms or something. So this is probably something we'll go back to so that you guys can see, visualize a third vector that is orthogonal to any other two vectors in space, because it is possible to, in 3D space, because it is possible, but only in 3D space. So this is not possible in 2D space. It's a three-dimensional thing. So again, the cross product of two vectors computes a third vector. So a vector that is orthogonal to both original vectors. Okay, original vectors. Okay. The formula for this, like I mentioned, it's a little complex, and I'm going to talk you through it. This is another thing that it's hard to do without physically being in front of you, because I do use my hands and arms to help show you this formula. But instead of my hands and arms, I have this handy dandy, hold on. Okay, well, I was going to use this thing. That would represent a finger, and you do need a finger when you do cross product, but I'm going to have to do another one because it won't let me move that without moving everything, so let's ignore it. Okay, here's my new guy. Okay, perfect. So I want to be able to move that around. Okay, I'll use that in a second. Okay, cross product. Here is the formula. Actually, before we get to the formula, we use matrices, a single matrix, to set up the representation of our two vectors that we're computing the cross product of. So here we're doing cross product of u cross v. So we would set up a matrix, u1 in the top row, or vector u in the top row, u1, u2, uv, u3, not v. It's late right now, you guys, so just bear with me. Okay, and then in the bottom row, it's v1, v2, v3. So we set these up just as a way to organize each of the entries in the vectors. All right, and now for the formula of u cross v. Okay, again, this produces a third vector. So to compute each of the three components, there's a little bit of work involved for each one. So to find the first component in the cross product, that's meant to cover up those two entries, and instead it's just going behind it, so that's great. Okay, I'm just going to roll with that. So that'll still help us visualize what we want to do. So to find the first entry, the first component, whatever, of the cross product, you cover up the first column like this. Once you cover up the first column and then you're just seeing these last two columns, then you compute one of the cross products. So to do that, you do this cross product, U2 times V3. So we multiply those diagonals together. So I'm going to write down the formula, U2 times V3, and then you subtract the other product. So now we did this product, and we're going to subtract that product, V2 times U3. V2 times U3. Do not get hung up right now on the letters and numbers. This will solidify a little bit more when we're working with actual values. Okay, the second component in the cross product now. So what you would do is to compute the second one, you're going to take your finger and cover up the second column. So whichever value in the cross product you're looking for, that's the column that you actually hide. I usually use my fingers to show this, or like my arm over the smartboard. So again, I know this little blue bar doesn't cover it, but again, so we want to focus, we're covering that, we're focusing on the first and last column. And we do the exact same product. So we do U1, let me find my little pointer, we do this cross, we get that product, and we subtract that product. So that would be U1 times V3 minus V1 times U3. The only change with this is that whole thing, once you get that whole product, is negative, but only in the second number in this. And then the last one, again, we would take your finger, cover up the last column. So we're looking for the last entry in this matrix, and we would cover up the last column. We do the same product. So this would be U1 V2 minus V1 U2. U1 times V2 minus V1 times U2. So you get all of those different products, find their differences, and that computes the cross product, which again results in a brand new vector that's orthogonal to the original two. Okay, so let's actually move on to an example of this. So down here in example 5, so here we have two actual vectors, and let's walk through this so that hopefully this will make a little more sense to you guys. So we have vector u, we have vector v. We want to compute vector w, which is the cross product of the two. The first step, again, is set these two vectors up in a matrix. So u goes on top, the first one that you're multiplying, so u would be 3, negative 1, 2. The second one, vector v, is 4, negative 5, 6. Okay. All right, so the cross product here of u cross v, it's going to result in another vector, so I got my little brackets, and I want to find the first component in that, so I'm going to cover up the first column. Okay, so then I'm going to do the cross product. So negative 1 times 6 minus negative 5 times 2. So negative 1 times 6 is negative 6 minus negative 5 times 2, which is negative 10. So I'm going to subtract negative 10, which means I'm adding 10. That's how I will compute. So if we want, we could even just simplify this as we go. So negative 6 plus 10, and we get a positive 4. So that's the first value in our new vector. The second value in our vector, I'm going to cover up the middle column with my finger or bar or whatever you have, pencil. And then we are going to do the same thing, but remember the whole thing is negative for the second one. We negate whatever value we get when we do the products. So I think it helps to just put that negative out front right away and then continue. So we have 3 times 6, which is 18. Yes, it is 18. And then we subtract 4 times 2, which is 8. So we end up with negative 18 minus 8. So 18 minus 8 is 10. Negate it, and our second value is 10. For the third value, we cover up the third column and continue. So that would be 3 times negative 5, which is negative 15, minus 4 times negative 1. So minus negative 4 would be plus 4. And so the final value is negative 11. So this cross product results in this new vector that is orthogonal or perpendicular to both of the original vectors. Okay, so in number 6, we want to verify that W is orthogonal to U and V. So we're still using the vectors from number 5, and we're just going to prove that they are orthogonal. So we need to think back to how do we prove that two vectors are orthogonal, and that is the dot product must be 0. So dot equals 0. That's what I mean. The dot product between W and U must be 0, and the dot product between W and V must be 0. I cannot move down because some of my text sticks where I want it to, and some of it doesn't, and I cannot figure that out. So I just need to put it all back and use this tiny space at the bottom. So I apologize for that. Still working through some of these technical things here. Okay, so first I need to do W dot U, and then I'll do W dot V. So just the dot product of W, so that would be 4 times 3, so that's 12. Negative 10 times negative 1, so that's positive 10. And then negative 11 times positive 2, that's negative 22. So we add all those up, we've got 12 plus 10 minus 22 is 0. So that's how we can verify that U and V are in fact orthogonal. Then we'll do the same thing with V and W. So W dot V, let me switch colors again here, would be, so now we are dealing with W and V right here. So 4 times 4 is 16. We add that to negative 5 times negative 10, so plus 50, so we're at 66. And then we add negative 11 times 6, which is negative 66, which gets us right back to 0. So it's a quick way to show that, yeah, we've computed the cross product correctly because this is, we've proven, is orthogonal to the original 2 by computing the dot product. So you can see how cross product and dot product are related, but they are different things. Cross product results in a third vector, and it's orthogonal to the original 2. Dot product results in a single value, an integer, and that is either 0 or not, and if it is 0, then it is, the two vectors are orthogonal. Okay, well, I'd like to come down here to this last one, but I got a bunch of stuff going on, so let me just get rid of it all. I don't know why this does this sometimes, and sometimes it does not. Okay, so this last one, find a vector t orthogonal to both U and V. So first of all, this is basically asking the same thing we've already done in number 5, but the reason it's on here is because it's worded differently, and that's an important difference to make note of. I'm trying to clear this up so we can actually see. Number 5 says, here are two vectors, find W, which is their cross product. It specifically has the cross product notation. In number 7, it says, find a vector t orthogonal to U and V. So it doesn't actually say compute the cross product, but in order to find a vector orthogonal to two other vectors in 3D space, you have to use the cross product. So that means we need to do U cross V to get a third vector T. So again, the setup, we always set this up with a matrix. So 0, 9, negative 4, 7, negative 1, 3, and we will compute the cross product with the same formula I showed you guys above. Okay, so to find the first one, we cover up the column 1, and we would do 9 times 3, which is 27, subtract negative 1 times negative 4, which is positive 4. For the second entry, it's always, we negate the value we end up with, so I'm putting that negative out there first. I'm covering up the middle column, so I don't have my little bar to cover up that middle column. Honestly, I'm just holding up my pinky. Sometimes just to visualize that. 0 times 3 is 0, and I'm subtracting 7 times negative 4, so I'm subtracting negative 28, so that would be plus 28. The third entry, I'm covering up the final column, and I have 0 times negative 1, which is 0, 7 times 9, and I'm subtracting 63. All right, so we get all these values. We end up with 27 minus 4, which is 23. We end up with 28 here, but we negate it, so it's negative 28, and then negative 63. So I know I went through that one pretty quick. I just wanted to reinforce the process and give you guys a chance to look at one more example. Okay, I'm going to stop here, and I anticipate questions on cross product when I get back. If you have any issues, definitely make note on your homework. Your assignment now, I want you to finish the 11.1, 11.2 worksheet. Hang on to it though, and I'll collect it next time I see you in class.